Okay, I'd like to thank the organizers for inviting me. It's a very interesting venue. This is going to be a sudden grinding change of gears from everything that's happened so far. You'll see this has quite a different character, and I'll make some probably very contentious claims, and hopefully we'll have some time to talk about them. So let me go to the beginning. What is physics after all, which turns out to be a much more contentious question than it ought to be. It used to be, when I was a sprat, that you'd hear things like this, that physics is the theory of matter in motion, which gives you a nice flavor for the thing. It tells you it's awfully universal. It tells you that all biological systems are also physical systems because whatever else they are, they're matter in motion and so on. But you could object to it. You might say that it's not really clear that everything that's physical should count as matter. Things you think of as physically real are, suppose you believe there are quantum states. So I said quantum mechanical wave functions there, but quantum states, something that corresponds to the wave function, are real. Do you want to say they're material? The word matter is a little vague here. And it's not quite clear that the only things these entities do is move. So if you were Democritus and you thought all there were shaped atoms bouncing around in the void, you're pretty well covered with this definition. But you might say there are changes that don't really count as motions. So you could update this thing a little bit to be a little safer, that physics is the theory of what space-time, entities in space-time, which is what Bell would call the local beables of the theory, and entities that interact with them are, and what they do. So the main bumper sticker is physics should tell you what there is and what it does. Now, what we practice, as everybody now knows at the end of today, is mathematical physics. So what's that? It's physics that uses mathematical structures as representations for physical entities and physical states. I take that to be a fairly uncontentious definition. It's really important to think about this a lot. That is, the role of mathematics in physics is the medium of representation, the way that natural language is the medium of representation in novel writing. Or in history, to be, hopefully we're doing something more than writing novels. So say if I'm a historian. And the problem here, and this is an absolutely endemic problem to try and even talk about these issues, is that systematically the language has been run together. Language describing the mathematical objects, which are abstract, and the language that's supposed to be about the physical things, which are not abstract. So for example, I'm going to give you 3 sentences which I think anyone who knows this kind of stuff could hear and not feel at all worried about any of the 3 sentences. So you're looking at an experiment and you say, the electron reacted to the electric potential. And then someone says, hey, what is an electric potential anyway? And they say, the electric potential, that's a scalar field. And being an annoying person, they say, what's a scalar field? And you say, a scalar field is an assignment of real numbers to space-time points. And then you sort of run those 3 together and you say, wait a minute, the electron just moved because it interacted with an assignment of numbers to space-time points. And that's not right. That makes no sense at all. Nothing is going to get deflected by an assignment of numbers to anything. So what's the problem here, right? This is the kind of thing, as a philosopher, your ear becomes very highly attuned to. The term scalar field is so ambiguous between the mathematical thing, which is an assignment, it's a function, right? It's an assignment of numbers to something, and to scalars, right, which are numbers to something. and the thing it's supposed to represent, which is presumably not an assignment of numbers to anything, that I don't know what scalar field means, right? I can't say that one of those meanings dominates over the other. This happens, by the way, in spades in quantum mechanics with the wave function. People ask, is the wave function real? And again, you have two things. You have a function, which is obviously a mathematical thing that we call the wave function. And then there's an open question whether there's a physical thing that it is supposed to represent. I prefer to call that the quantum state. So often the discussion about is the wave function real, in my terminology, you have a perfectly good question like, is there a quantum state after all? But if you're using the word ambiguously between the math and the thing the math is supposed to represent, the conversations can easily become very confused. What's the structure, according to me, and man, is this an unpopular definition, of a proper physical theory? It should be a clear, and if we want a clear and unambiguous physical theory, is not simply a mathematical formalism, right? A piece of mathematics is, whatever it is a piece of mathematics. And that's it. It's not a physical theory of anything. If I give you a mathematical formalism and I add to it rules that tell you how to use it to make predictions, that also, according to me, is not a physical theory. It's a kind of prediction-making recipe. And it may be good, it may work well, it may work poorly. If you think about the Osiander's preface to De Revolutionibus, when he's sort of presenting the Copernican theory, he was very explicitly being instrumentalist about that theory, saying, do not take it seriously, right? Don't think that I'm giving you a story about what's really going on. I'm giving you a way to calculate, make predictions in positional astronomy. It may be simpler and more accurate than the one you've been using. I am not saying the Earth is actually rotating on its axis. I am not saying that the Earth is actually orbiting the sun. Of course, Copernicus was saying exactly that, but Osiander was trying to keep him out of trouble. That's what it is to be an instrumentalist about a theory. But Copernicus really had a theory, right? The theory was not just the predictive apparatus. What was the theory? Well, the theory, the Copernican theory, gives you a clear as you can, precise physical theory is a mathematical formalism together with what I'll call a commentary on the formalism. And what's in the commentary? So I'm going to make a little suggestion here, which no one is ever going to adopt, but I'll show you why it might be a useful suggestion, about how to put the commentary on the mathematical formalism into what I'll call a canonical form. Just a structure that you can take any physical theory you want to talk about, any theory of mathematical physics you want to talk about, and just put the commentary on it into this structure, and it helps make clear what the theory really is. So what's the commentary supposed to do? It's supposed to specify, first of all, the fundamental non-derivative ontology of the theory. Okay? So that is, what does the theory postulate to exist? And it's not an accident that John Bell invented the word beable, which is just the Anglicization of ontology, right? Ta onta are the things that exist. And so he took be, right, the things that are. So the beables, what Bell meant by the beables of a theory is just what we normally mean by the ontology of a theory. So you should tell you, what does your theory postulate to exist? This is also a bit like Detlef Durr's question, what is your theory about? When you do that, you could at the same time give a general account of what kinds of things these are. So you might make a distinction, as Bell does, between local beables and non-local beables, right? Where the local beables, in some sense, are elements that exist in small and restricted regions of space-time, And the non-local beables, if any, are things that don't. Like, if there's a quantum state, if there is a physical thing that corresponds that the wave function is representing, it's not a local thing. It should specify which of the mathematical entities that are in your formalism are going to be used to represent that fundamental ontology. At this point, you could add some purely mathematical remarks about the mathematical structure being used, and we'll have an example of that in what we're going to run through. It should contain, and this is a brand new word I just made up, a nomology from nomos, from law, right? So just as you want the ontology is your account of what exists physically, the nomology is what is the account of the laws, the fundamental physical laws that you're postulating. There's a connection between the ontology and the nomology, which is that the laws should be stated mathematically only in those mathematical terms that you've already told us represent the fundamental ontology. And it's at this point that a bunch of the main force of Bell's against measurement and the main force of people saying there is a measurement problem arises because measurements are not fundamental physical things. They may be physical things, right? A measurement, you might say, is just a physical interaction of a certain kind. That's fine. A chair, right, is a physical thing, but it is not a fundamental physical thing. It is a composite physical thing. And so the word chair should not appear in the laws of physics. You would be in a lot of trouble if the word chair appeared in the laws of physics, because you take a chair and you start chipping away at it bit by bit. And like Theseus's boat, at some point it ceases to be a chair. But there is no particular point where that happens. And if the laws of physics depended on whether it was a chair or not, they wouldn't know what to do, right? And if the laws of physics had to know whether a measurement was being performed in order to know whether it should collapse the wave function or continue a nice linear evolution, the laws of physics will not know what to do, because there are all kinds of physical interactions that are neither obviously measurement enough like or not measurement enough like to count as measurements. That's why Bell against measurement was against, it's against the word, right? Against, quote, measurement. And not even as a bad word in itself, but not as a word that should appear, as Bell said, in the formulation of a professionally precise physics. And he had a lot of other words, microscopic, macroscopic, reversible, irreversible, a lot of words that he says are not sufficiently sharp to appear in the statement of a fundamental physical theory. Good. So if you did it this way, that you had to first tell me what you're saying exists at a fundamental level physically, and then only write the laws in terms of that stuff, you never would have had the measurement problem, because nobody ever would have attempted to write laws that had the word measurement in them. Okay. You can have in this a derivative ontology. So as I say, if the fundamental ontology were, say, electrons and quarks and so on, but you say, gee, there's, in a certain sense, lots of things in the world that we may want to talk about that are not individual quarks and electrons, but they're somehow compositions of them or derivative from them, that's fine. You can define and explicate these derivative things. You'll see an example. I mean, this is kind of abstract, but you'll see the example I'm going to give. And you should say how the derivative ontology derives, presumably by a mathematical function, from the fundamental, well, the representation of the fundamental ontology. And you can talk also, and this will be relevant for our topic here, about mathematical pseudo-entities. They're pieces of the mathematics that don't represent anything physical at all, although if you were being careful, you might trick yourself into thinking that they do, and you might explain what they are, why they're useful for some calculational purposes, and so on. Okay, so that's the way I think a proper physical theory should be presented. So there's a proper, more or less proper physical theory we've all seen. You can work your way backwards from the laws to the fundamental ontology, because what I said was that the laws should only mention things that are in the fundamental ontology. So if this were in canonical form, this would be okay. You could just stare at those and say, classical electromagnetic theory, what is it? Well, here are the laws, and then I can sort of analyze those and figure out what it is in a certain way that this theory is committing itself to physically. Everybody's seen this. Now, one other thing this is going to do, as we'll see, is it's going to make you reflect in ways you maybe haven't before. When you start thinking about this question, how does the mathematics represent the physics? How does that relation go? Certain questions jump out at you. All of this stuff, actually, I'm talking about today, I've never talked about this before. Well, I did a couple weeks ago, but basically I did all this work in the last 6 weeks because for the first time I was teaching a course on gauge theory, and we were just starting out with classical electromagnetic theory, and it's the first time I taught it. And everybody knows you think you understand something until you have to teach it. And then all of a sudden, like all of these huge gaping holes of ignorance that you have jump out at you, because you say, but what if the student asked that? And you say, yeah, well, that's a good question, right? All these questions came up, and this is the result of that. All right. So what would the fundamental ontology be if I took Maxwell's equations in this canonical form, which is due to Heaviside? Apparently there were 20, Maxwell wrote down 20 equations, 12 of which aren't even considered part of electromagnetic theory anymore. And it was Heaviside and some other people who gave it that canonical form. And notice, and we'll talk about this too, that canonical form is written in a mathematical formalism. And you have to think, how is that formalism working? All right. So if we take those to be the nomology of the theory in canonical form, then we can just read off the mathematical representations of the fundamental ontology, and what we would get is that there is something we call the electric field that is represented by this vector field E. There is something called the magnetic field, which is represented by this vector field B. There is a charge density that's represented by a scalar field rho. There is a current density represented by a vector field J. There is a time structure that's represented by the T, and there is a spatial structure that's represented by the vector R. And that's what we have in that particular. Now, that's just Maxwell's equations. To really finish this off, as we'll see, you need like the Lorentz force law and Newton's equations. And we're going to throw those in at the end, but right now I'm just focusing on electromagnetism. Okay? So if I just stare at the mathematics, and I know at least this much about the mathematical formalism, that those are the fundamental physical things this theory is about, the math will suggest things to me, right? That is, it'll be very natural to read the mathematics as telling me something about these physical items. And in a well-chosen mathematical representation, and you can have the same theory, what we would normally say is exactly the same theory presented in different mathematical guises, as we know. You can change the mathematical language. And each of these mathematical languages will be suggestive of a certain understanding of what the physical world that's being represented is like. And one thing that's sometimes very useful to do is just to think, can I restate this theory in another language? Can I restate it in yet another mathematical language? Can I, and this is something else I've been doing for the last 5 weeks, invent a brand new mathematical language? I won't take you into that. A brand new mathematical language to present the same theory because they will give you different suggestions about what the world might be like. The mathematical language being used here is vector calculus. And basically, we have two gadgets for representing physical things, scalar fields and vector fields. And we represent the vector fields with the bold. And so you might think, well, that duality of the mathematical apparatus is reflecting a kind of duality in the physical world. There are physical things that are scalar. Again, now you hear now the ambiguity of scalar field, right? There are physical things that are scalar fields, meaning what? Meaning there are physical things that at each point in space-time have one physical degree of freedom. And so just by handing you a single number, if that's an appropriately calibrated number, I can nail down what that degree of freedom is. And there are vector fields that somehow have 3 degrees of freedom at every point, and I often visualize that in terms of pointy arrows, right? That I can't just give you a magnitude, I have to give you a direction. You can think of the 3 numbers as one of them giving you the magnitude and the other 2 giving you angular directions. So then the vector fields look like little pointy arrows in your head. There's this use of the cross product. Now, this is all going to seem like really weird. Why am I talking about this? This will be clear in a second. There's the use when you actually write down the equations of this cross product, and you would say, OK, if I need the cross product to write down the laws, I guess the laws should only make sense, or the quantities that I need to talk about to use that should only make sense in a setting where the cross product itself, in some sense, makes sense. Why the cross product? Well, because we've got curls, right? When you write down Maxwell's equation, you have to talk about the curl, and you have to talk about the divergence of your vector fields. And the way we represent the curl in this notation is by a cross product with nabla. So you then might ask yourself, well, what's that all about? What's this mathematics telling me? What is I have a vector field, and now I want to talk about the curl of it. What is that, right? And I want to talk about. So this is something that, again, maybe everybody in this room has figured this out. I hadn't figured it out, and the word curl or roticity. You have this image in your head of a vector field as a bunch of arrows, right, in space pointing some way, and you say, OK, the curl is somehow telling me how curly they are, right, how much they somehow are rotating, or if they have nice flow lines, right? If I integrate through and get flow lines, the curl is a measure of how much those flow lines are twisting and curling. Then you also have that's sort of one question. Another is, what is this deal with this cross product that I'm using? Right? It's important in the statement of the nomology. Again, we have the same question. We've got the same nabla dotted into E and B. What do I mean by the divergence of a vector field? Right? What does that represent? And normally, with the divergence, just the way you think of the curl as somehow telling you about the twistiness of these arrows, you think of the divergence as telling you about sources and sinks, right? So if all the arrows are pointing into a region, or better, if all the arrows are pointing out of a region, it's got a divergence. That means there's a source. If you think of the arrows as the flow of water, it means there's a source there. And if more arrows are going in than going out, you have a sink, and you have a convergence rather than a divergence. So you have a sort of a picture in your head of what the math is about. Now, something weird about the curl. Right? There's something a little surprising about the curl itself, and then there's something even more surprising about the way we represent the curl. So let me just go, this is going to strike you as, I probably already think I'm crazy. But I want you to get in the mood of noticing little tiny things that you never noticed before. At least I never noticed before, because you learn them so early. And you learn them by rote when you're just beginning to learn mathematics and just beginning to learn physics, and your job is not to question anything, but just to suck it all in and spit it out on the tests, that you get used to it and you don't sort of think about what does it mean. So what's weird about the curl? Let me try and convince you there's something a little weird about the curl. So as I say, in the Heaviside representation, we define the curl as the cross product of nabla with a vector field. And that gives us yet another vector field. So it's a kind of operation. So this is actually where I began when I was teaching this stuff. I said, let's just think about these operations. What does the gradient do? OK, it takes in a scalar field and it spits out a vector field. And what does the divergence do? It takes in a vector field and it spits out a scalar field. What does the curl do? It takes in a vector field and spits out a vector field, right? But when you learn, everybody knows when you learn how to take cross products, you learn the right-hand rule, which, again, probably everybody thought it was a little weird, right? What's special about my right hand? So there was something strange about that. But there's something even much more strange about it, about this mathematical representation. So let's first talk about what the curl is physically if I think of the vector field as a representation, natural representation of something physical, which is what I'm using this math for. So if you think of the curl or the roticity of the field as talking about the twistiness of the field of the field and of the integral curves, you'd say, can a field with perfectly straight parallel flow lines have a curl? And your natural reaction is, no, of course not. The curl measures the twistiness. And if all of these flow lines are absolutely dead straight and parallel, nothing's twisting, it can't have a curl. Like, this is a river. Nice laminar flow of water. It's slower, right? The river water is slower toward the banks and speeds up and gets really fast toward the middle and then slows down toward the other bank. And, something called the curl, you'd say, that thing shouldn't have it. But it does, right? That vector field has a curl. And, there's a nice book, Div Brad Curl, and the guy who wrote it, this is one of these things, you read a whole book and there's one sentence and you go, wow, that makes sense, right? One of those little nice moments. And he said, no, you see, here's how you tell whether you've got a curl. Yeah, think of this as a flow of water. Now take a little paddle wheel, right? A little thing with just propeller things coming out on the side, and stick it in the current and see if it spins. And if it spins, there's a curl. And it's really obvious then that, yeah, there's going to be, if I stick it here, there's going to be more pressure on this side than on that side, and it's going to spin that way. And if I stick it here, it's going to spin that way. And if I stick it dead center, it's not going to spin at all. So immediately I know, yeah, there's a curl to that field, and it's zero in the middle, and it's one type of curl corresponding to clockwise and another type corresponding to counterclockwise along the sides. And the way I have it there, you'd even say, gee, it's probably a constant curl, right? Because this pressure differential looks constant there. And that's right? That's the right answer. So that was really cute. I liked that. But then I thought, wait a minute. If I'm a little two-dimensional guy, and I live in a little two-dimensional world that has two-dimensional rivers with two-dimensional water flowing through it, and the two-dimensional water happens to be flowing like that, I live in a world, a two-dimensional world with a curl, and I can't use my right hand to implement the right-hand rule, because I don't have anywhere for my thumb to stick out, right? I can't. So there's something incongruous about this particular piece of mathematics. there's something off. There's something a little weird about it. Right? Two-dimensional worlds should be able to have curls in them. Some people know there's different ways you can go. This is why I say I'm now inventing a new geometrical way of doing things where you would not be at all surprised that a two-dimensional world has curls in it, because they're obviously two-dimensional objects. But I won't get into that. So let's at least take the cross product out. I could go on and on about the problems of using vector calculus, but I want to get to a different point here. Let's take the cross product out and just write these now in a slightly more abstract form. So all we know about div is it's some function that takes in vector fields and kicks out scalar fields, and curl is some function that takes in vector fields and kicks out vector fields. And so, and if I no longer write the curl as nabla across anything, then you'd say, yeah, a two-dimensional world, they could have these equations without a problem, as long as I understand properly what a divergence and a curl is. So that's one thing that, again, I'm just getting really down to the basics. So, I mean, maybe I should say, I think physics has gone is following the following wrong route, which is that people seem to think nature is a really, really, really fancy mathematician, right? You have to learn non-commutative geometry and topos theory and God knows what to get to the physics of the quantum gravity. I have exactly the opposite view. I think the world is kind of dumb. In fact, this whole mathematical thing I'm talking about, all you ever have to do is add and subtract. That's it. Nothing fancier than that. I don't think the world is such a fancy mathematician. I think there's maybe a problem if our mathematics is getting a whole lot fancier than the world is. There are some ontological moves you can make. Once you've put things in this standardized form, you can make some ontological moves. So for example, the way I had that written out, there was a current density. But what is a current supposed to be? An electric current is just supposed to be the motion of the charge density, rho. And we needed, I didn't have it on that list, but it's going to be defined in terms of the space and time structure. We're going to need a velocity vector v. I mean, you certainly know you need it in the Lorentz force law. So you say, maybe I shouldn't think of J as being a fundamental thing. It's a kind of derivative thing. And so I've got this equals sub on. So that's ontological analysis, right? What J really is just rho in the direction of v, okay? At the speed of and in the direction of v, where v is the velocity vector field that's associated with the charge density. Now, I could go on for yet another lecture about how weird it is for there to be velocities associated with continuous densities, because particles, you know what their velocities are, right? Because they've got nice world lines that have nice tangents. But densities aren't like that. They're mush, right? What is the velocity of a density? I mean, what determines its velocity? I would like, it's much easier if at the end of the day at the bottom you have particles, point particles moving, and when you talk about rho, that's always at a macroscopic scale and you're averaging, right? But let me leave that problem apart. We've got enough to deal with. The other thing is, my own view is that the fundamental laws of nature, well, my own view is that there should only be one. Ultimately, there is one fundamental law of nature, and that it is fundamentally a dynamical law which tells you how things evolve in time. And you might notice that of the four Maxwell equations, two of them don't mention time. One of them is this div E equals rho. That's not a dynamical law. You could also take that as a kind of ontological reduction. You could say, look, maybe charge just is the divergence of the electric field. If I'm already committed to an electric field, and I understand what it is for a field to have a divergence, maybe I should think of this not as it were, an equation that connects two fundamentally different things by law, but as an equation that's telling me what one of the sides is in terms of the other, right? And if I have an electric field, it's already got a divergence. It's just there. It is what it is. So let me just say that's what rho means, right? That's what rho is. So I move that out of, so I'm talking about ontological moves. I move that equation out of the nomology, it's no longer a law, into, all right, I'll go more quickly, into another category. Similarly, for a div B equals 0, you could say, look, that's just a mathematical way of saying there are no magnetic monopoles. It's not a dynamical law. You can regard it as a mathematical expression either of the physical impossibility of monopoles and absorb it into the conventions, or you can accept it as a contingent fact. So there are lots of ways to do this. Now what I want to do is talk quickly what everybody knows about the scalar and vector potentials. In classical theory, they're regarded as mathematical pseudo-objects. The existence of the scalar and vector potentials, A and phi, follows by purely mathematical considerations for any E and B, so long as div B equals 0, and we have that in the nomology, so we're guaranteed of that, and so long as the curl of A plus E plus dA dt equals 0, and we're can make sure that that's right. And so we know that as long as we have E and B that satisfy the equations, A and phi will exist. But we also know that not only will one such pair of A and phi exist, but if one does, then there are an infinite number of other ones that do exactly the same job in reproducing E and B, right? And we can, so if you give me an A and phi that work, if I add the gradient of any arbitrary scalar field psi, and I guess that shouldn't be bolded, sorry, and that make this transformation, I'll get another A prime and phi prime that do the same job. So there are an infinite number of these A phi pairs, and we say that they're all related by a gauge transformation, and that's merely a gauge degree of freedom. It doesn't represent a physical degree of freedom in the system. So from all this, we can get classical electromagnetic theory version 1 in various types. So here is a canonical form of a commentary. Here's what the theory is called. Here's what the physical ontology is. Here's what the mathematical representation is. The purely mathematical facts tell you about the existence of the A and phi. I've left out the talk about space and time, but we have enough on our plate. There are the fundamental laws, including the Lorentz force law and Newton's law, and we have the scalar and vector potentials as mathematical pseudo-entities. That's a way to understand that mathematical formalism. But I can make these moves, right? I can, as I say, I can take J out of the fundamental ontology and make it a derived thing. So J equals rho V gets moved over into that column. I drop it out of the nomology. I now have one less law. I can make the other move, which is to say div B equals 0 is just a way of saying there are no magnetic monopoles. That drops out of the nomology, right? I'm told that that's what that equation expresses, and now I have one less law. And I can do both of those things and get my nomology down to just from the 4 original Maxwell laws down to 2, and I still have Newton's laws there. So you see what I'm doing, right? So each of these, in my view, are different theories, different physical theories using the same mathematical apparatus with different commentaries. Now, we know about this. So this is discovered in the lab, that we have the Aharonov-Bohm effect. Changing the magnetic field in the solenoid has a visible effect on the interference fringes. And from the paper, it's a beautiful paper, right? A really beautiful paper. They say exactly that in classical formalism, you use the potentials, but they don't appear. Notice, the fundamental equations of motion, they say, the fundamental equations of motion can always be expressed directly in terms of the fields alone. A and phi don't show up in the nomology, or don't have to anyway. They don't in the way that's normally presented. But in quantum mechanics, you seem to need to mention A and phi, which should strike you already as a little odd, right? If what's really real is E and B, why do I have to talk about A and phi? And then they say, now we're going to show that actually there are empirical indications that A and phi are physically real. So now we say, let's just take that hint and now put over here, instead of E and B, put A and phi. There, now in my fundamental physical ontology, I have to rewrite everything here in terms of A and phi. And here I do nothing else, which what does it mean? I no longer have determinism at all. I have a radical kind of indeterminism, because everything that I thought of before as just a gauge transformation is now a transformation that changes what the physical things are doing. And specifying what A and phi do up to any time leaves open an infinite number of ways for A and phi to continue after that time, which is what we normally think of as constitutes changing gauge at that time. So the result of taking A and phi seriously and not doing anything else leads to radical indeterminism. That doesn't sound too good. So I want to get rid of that. So what do? Well, here's something I can do. I can gauge fix. I can gauge fix many different ways. One way is with Lorentz gauge. And again, I only just found out that Lorentz is not Lorentz. And the Lorentz gauge, although it fits with the Lorentz transformation, they're two different guys. I didn't know. There's a lot of mistakes about that. And here's the definition of, so I say I still have these sort of mathematical degrees of freedom. I can cut them down by putting on extra constraints. So I put on this gauge constraint. That turns out not to nail everything down. To really completely gauge fix, I have to put a constraint on phi as you go out away infinitely far, at least in an island universe. And then I get back now determinism again, okay? And if I also, my nomology, which before had laws that were mixed between A and phi, they've now become separated. And both A and phi satisfy laws that look very similar, both using the D'Alembertian. And you say, that's really pretty. That's the mathematics yelling something at me. I don't know what it is yet, but it's telling me something. Let me think about that really hard. Version 7, I do the same thing, but I just have added over here. I can now take one of my laws out and move it over here to say, really what I have here is, again, the definition of minus rho is just the D'Alembertian of phi, which I have over here. And so I got rid of rho here. Okay, so that's my 7th version. But there are other ways to gauge fix, right? So here's the 8th version where I've gauge fixed using Coulomb gauge. And that's nice, first of all, because it's a complete gauge fix, right? It's a complete gauge. You have no further, once you've imposed div A equals 0, you're done. And furthermore, for calculation purposes, it's nice because now phi, the electric potential, is just the Coulomb potential calculated instantaneously for the distribution of charges throughout the universe. Yes? And so you get different equations over here. A is still a D'Alembertian equation. The Lorentz law is getting more and more kind of messed up down here, but we're not going to talk about that right now. And I can have, this is the last version, I can do the same thing and again derive the charge density, so I've moved the charge density from the nomology over here to the principles of derivative ontology. Now, this also, this is also screaming out at me, and this is the main point I want to make. So I said, if you go into Lorentz gauge and you see my fundamental laws, I've cleared out the other things, and the only fundamental laws I have are all D'Alembertian laws. And now, we all know enough relativity to say it's grabbing you by the lapels and saying, I am a relativistic theory, right? Because you can go into Minkowski spacetime and define the D'Alembertian like child's play, because it already has the right form, right? dx squared plus dy squared plus dz squared minus dt squared. So you can just convert this immediately into a form that lives in a relativistic space-time, and you know immediately that the original theory was relativistically invariant, and so on. And that's what everybody's done, because they thought, yeah, relativity, that's good. The thing I want to point out is, what if you went a different way? What if you said, I like Coulomb gauge better, right? It's a complete gauge. It gives me this nice, simple way of calculating phi, what's it telling you? It's telling you, you know, your A and your phi, they have a slightly different dynamics. The A part, the vector potential part, that lives naturally in a relativistic space-time. But the phi part, because you're calculating phi by the instantaneous distribution of charge, needs a foliation. The phi part needs a slicing, a global slicing, the kind that you got out of absolute simultaneity in Newton's theory. And so you'd say, if I want to adapt this, it would live very nicely in a space-time that did have a relativistic structure for A, and in addition, had something like a global foliation for phi. Now, Roddy mentioned, and it's a very interesting thing that he mentioned it, that if you want to do Bohmian mechanics in a relativistic setting, here's an easy way to do it. Add a foliation. Use the foliation for specifying the guidance equation. You don't need it for specifying the Schrodinger equation, okay? And our division between A and phi here is now looking like a division between the dynamics of the quantum state and the dynamics of the particles that are directed by the quantum state. Now, you might say, why should I do that? Now, there's no reason to do it until you get Bell's theorem, right? So they wouldn't have done it in 1959, even having noticed this. So part of this is, what happens when I take A and phi seriously mathematically as representatives of what's physically real? But in 1959, you would not be tempted to do this. But after 1964, you ought to be really tempted to do this and say, it was sort of built in all along. That picture, that's a possible picture of the world. And everybody who says, but relativity, we must need a relativity, why would you think that Einstein would have gotten everything right about space-time before Bell? Before everybody knew you needed something non-local. He wasn't trying to explain anything non-local. Why think that relativity theory got to the very bottom of space-time structure and cannot be touched when you think about when it was developed and for what purpose, and what needed to be explained by it? So this is the kind of thing I think, if you get really clear about what you're doing, so the other thing is you could say, I don't like Lorentz gauge because I can't even gauge fix if I'm not in an island universe, and I'm not in an island universe, so that's not ideal, okay? So as I said, Lorentz gauge is screaming out, I am relativistic, and Coulomb gauge is screaming out, I live in a relativistic space-time with an additional foliation. So I have some quotes from the, how much time do I have? Have we gone over already? -4. Okay. The rest of this, so let me, instead of reading this is all from the original 1959 paper. It's a beautiful paper, right? It's one of those papers, you read it and you understand it, and it's, it says this is really important, pay attention. We've been thinking about electromagnetism wrong all this time. You all learned it wrong, and you all learned to think about gauge transformations in A and phi wrong. So these are just all, there are things that are here about searching for new beables. There are things about what possible responses can you have and what would the costs be. And I had wanted to read that, but there's not enough time. So we should have applause for the authors. This is David Bohm's centennial, as we know, and I don't know if Yakir is here, but there they are. I said, applause for the authors. This is a beautiful paper. And I had to hunt around. I didn't get anywhere near a picture of Aharonov at the age when he wrote this, and I'm sure this is later for Bohm. It was about the nearest thing I could find for Bohm. They were younger, okay? So I said to my wife, I feel like I'm going to the opera here. There's all these old people and then a scattering of young people. This is work they were doing when they were young, and they were, willing to shake things up a bit. And I hope the young people here take a clue out of that. So that is it.